Okay, I'm recording. Any questions about the 3 problems for homework due today? Okay, don't forget test 1 is on November 9th during class, and the review for test 1 is on November 4th during class on Zoom. Okay, so review is November 4th, and the first test is on November 9th.
I have a quick question.
Yep.
So how do you, for number 28, how do you go about doing the Kramer's rule for a 4x4 matrix?
Okay, so so you're just using, you have, in our example class, we had a matrix A, A1, A2, and A3. Now you just have A1, A2, A3, A4. So so for 2.3, number 28. Okay, so so you have the system there in front of you, right? So this is going to save time. So I have the book in front of you. You see the system there. So your coefficient matrix A is going to equal the coefficients in that linear system. So let me just make this 4x4 matrix first. Okay, so the coefficients of that matrix for 28 are -1, -4, 2, 1, 2, -1, 7, 7, 9, -1, -1, 1, 3, 1, and it's okay. And then 1, -2, 1, -4. Okay. So so A, right? That's the coefficient matrix A. That good so far?
Yeah, then I wasn't really sure what to do after that.
Okay, so for A1, you have another 4x4 matrix. Oh, yeah. Okay, so for A1, you have another 4x4 matrix. I have to copy this. I have to do this again. Copy. Okay, so for A1, what you want to do is you want to replace the first column with B. Little b is the column vector that consists of the constant entries. So little b is equal to the numbers -32, 14, 11, -4, right? So you represent the linear system by the matrix equation AX equals B. Okay, so A is the coefficient matrix and X and B is the right side. Does that make sense?
Yeah.
Okay, so for A1 is the matrix you form by replacing, because of the indice 1 here, you replace the first column with B. So it's -32, 14, 11, -4. So that's the first column. Then the rest of A1 is the same as A. So the second column is the same as the second column of A. So it's -4, -1, 1, -2. The third column is the same as A, so it's 2, 7, 3, 1. And the fourth column is 1, 9, 1, -4. Does that make sense?
Yeah, and then like for A2, you put in the second column, A3 in the third column.
And A4 is the fourth column, right? So similarly, similarly, you define. So it sounds like, okay, so it sounds like you get it. And so, right, so I don't need to explain it, you get it. So then you similarly define A2, A3, and A4, right? Okay, so that's that step, right? Now by Kramer's rule says that if the determinant of A is non-zero, then there is one unique solution to the linear system given by the equations x1 is equal to the determinant of A1 divided by the determinant of A. X2 is equal to the determinant of A2 divided by the determinant of A. X3 is equal to the determinant of A3 divided by the determinant of A, and then X4 is equal to the determinant of A4 divided by the determinant of A. That makes sense?
Yeah, and then I was just confused how to get like the determinant for a 4x4 matrix, because I wasn't sure if we did that like in class.
So, okay, so if you want the determinant of a 4x4 matrix, so you want the determinant of this matrix. Oh, okay, I guess do like that. Okay. So you want the determinant of this matrix. So all you have to do is find a cofactor expansion along any row or any column, and that's equal to the determinant. So you choose any row or column you want, find the cofactor expansion along it, and then that is equal to the determinant of the matrix. So this is the matrix. I'm rewriting because it's a bar now instead of there's a unique 1, -2, 1, -4. Okay, so now you want the determinant of that matrix. So you take a cofactor expansion along any row or column you want. So let's take it along the first row. So we find the derivative. I mean the determinant of A using its cofactor expansion along its first row. Okay, so the cofactor expansion along the first row is if you take, okay, so you take the first term, which is -1, right? So we're going along the first row. So I'm going to label the first row in blue. So this term is blue. These are all the terms in the first row. Okay, so I'm moving along the first row in each of those terms. So this term, I'm going to take this term -1, multiply it by the determinant of a corresponding submatrix. Then it's going to be minus -4 because we're alternating sign. So then this is minus the term -4. It's times a corresponding determinant of a corresponding submatrix plus the next term 2, because the term is 2, not because it's plus it's plus the term 2 times its own corresponding submatrix, and then minus the term 1 in the first row times a corresponding determinant of. Does that make sense so far?
Yeah, then I know it becomes like a 3x3 matrix, right? But then I wasn't sure, do we have to break that down like a bunch of times also after that?
Yeah. So then so this is only, there's several steps, right? So below I'm just putting the checkerboard pattern here, right? You have a plus here, a minus there, a plus here, and a minus here. And so it's a checkerboard pattern. So to save time, we're gonna do all the minuses first, then the pluses. Okay, so when we move along the first row, we're taking pluses and minuses of the products. And so it's not because of the terms are plus or minus, it's because of the pluses and minuses in this grid. So we do the first row. So the first term is positive, the next row is negative, the next row is positive, next row is negative. Right? The first term does not have to be positive. If we chose the second row, then the first term would be negative. We'd alternate from there. But first row, the first term is positive. So it's positive -1 times that determinant minus -4 times the determinant plus 2 times the determinant minus 1 times the determinant, right? And now for each of these, there's a corresponding submatrix. And so these matrices are determined because if you take this entry -1, because here's -1, you remove the row and column it sits in. So you move the first row and first column. Sorry. So then you're left with this submatrix -1, 7, 9, 1, 3, 1, -2, 1, -4. Does that make sense?
Yeah.
Okay, and then the -4 has its own corresponding submatrix. And so if you move the row -4 is in and the column -4 is in, you're moving the first row and second column. If you do that, you keep the order of everything else the same. And so you have 2, 7, 9, -1, 3, 1, and then 1, 1, -4. Does that make sense?
Yeah.
Okay, and then for the next one, the term is 2. So you move the first row and the third column. So now you have the submatrix 2, -1. You jump to 9. Then you have -1, 1, jump to 1. Then you have 1, -2, and jump to 4. That makes sense?
Yeah.
Okay, and then lastly for 1, you move the first row and fourth column, and you have 2, -1, 7, -1, 1, 3, 1, -2, 1. Okay, so that all makes sense?
Yeah, it does.
Okay, good. Okay, so then you compute each of those determinants, right? And so when you have a 3 by 3, the checkerboard pattern for a 3 by 3 matrix looks like this. You have plus, minus, plus, minus, plus, minus, plus, minus, plus, right? So when you do each of those determinants, you have your own expression there. So I'm not going to worry about the colors at this moment. For the I'm going to not care. I've done that step, so I'm now going to ignore the colors and talk about a new step. So this is then minus that determinant, right? And so you have this determinant that would go here. This determinant go minus is a plus. This determinant goes here, and then that determinant goes there. So I guess to make things easier, I'll do this one step at a time. So I'm just doing very basic operation here. I'm just changing the signs, right? So now we have this, and so now it's just a matter of calculating each determinant. Okay, so you calculate each determinant and you plug those values in there. So this determinant is then equal to, so I'm going to try to do this quickly so that we can move on with this. So then, so now this is just a regular determinant of a 3 by 3 matrix. And so you have this 3, 1, 1, -4. minus the next term, which is a 7, times the determinant of 1, 1, -2, -4, plus the term 9 times the determinant of its corresponding submatrix 1, 3, -2, 1. And now this is equal to, so you have -1 times -12 minus 1, -13, minus 7 times the next determinant, which is -4 minus -2, which is -2, plus 9 times that determinant, which is 1 minus -6, which is 7. And so that's equal to 13 plus 14 plus 63. So if you add those up, you get 27 plus 63, which is 90. So that determinant is 90. Okay. The next determinant, so you would plug that value in here. And so what that is it's 90. And then this determinant, you also calculate. And so then this determinant is then equal to, I'm just going to keep doing the cofactor expansion along along the first row, okay, in every calculation. That way, I don't have to write down where the cofactor expansion is coming from each time. So you have 2 times 3, 1, 1, -4, minus 7 times minus 7 times this determinant, -1, 1, -1, 1, 1, -4, and then plus 9 times this determinant, which is -1, 3, 1, 1. So you calculate that, and so you get 2 times -13 minus 7 times 4 minus 1 is 3, plus 9 times -1 minus 3, which is -4. And so this is equal to -26 minus 21 minus 36. And that's equal to -47, -83. Okay, so that's equal to -83. So 47, 83. So that's -83. So the next one is -83. So that determinant is -83. And so you keep calculating determinants. So this determinant is equal to 2 times what did I copy? Oh, okay. It's 2 times 1, 1, -2, 4, minus -1 times this determinant, -1, 1, 1, 4, plus 9 times its corresponding determinant, which is -1, 1, 1, -2. And so this is equal to 2 times 6 plus 1 times -5 plus 9 times 2 minus 1 is 1. So that's equal to 12 minus 5 plus 9. And that's equal to 16. Okay, so the next determinant is 16. So a 16 goes there. Okay, and then the last one is the determinant of this guy. And so the determinant of this guy is equal to, again, using cofactor expansion on the first row. It's equal to 2 times 1, 3, -2, 1, minus -1 times the determinant of -1, 3, 1, 1, plus 7 times the determinant of negative 1, 1, 1, negative 2. So then this is equal to 2 times 1 minus negative 6, which is 7, plus 1 times negative 1 minus 3, which is negative 4, and then plus 7 times 2 minus 1 is 1. And so that's equal to 14 minus 4 plus 7. And so that's equal to 17. So the fourth determinant is 17. And so this is equal to the number 17. So when you calculate that, you get negative 90 minus 332 plus 32 minus 17. Okay, so you calculate that, you have negative 412, negative 412, negative 380, negative 397. Okay, that's the value I got. That makes sense?
Yeah, okay, so this is the determinant for A. So then we would have to do this 4 other times for A1, A2, A3, A4.
Right, but then you just plug in.
Yeah.
It's an easy problem. It's just a lot of calculations. Does that make sense?
Yeah. So like for the test, would we have to do like a 4x4 Kramer's rule matrix thing like this?
So if I give you an exam, it'll be an exam where you have plenty of time to do it. So if I feel there's problems that will take too long for an hour exam, then I wouldn't put them on it.
Okay, thanks. Yeah, because I feel like this would take like a while.
Okay, I'm not going to be specific about what problems I wouldn't put in an exam, but I'll tell you that you'll have plenty of time to take the exam.
Okay, thank you.
Okay.
Thanks.
So, okay, but that makes sense, right? Okay, so that explains that. So let's go to lesson. Okay. So you have a lot of material to cover, so we need to move quickly. So next is chapter 3. And so chapter 3 is on Euclidean vector spaces. Okay, so 3.1 is on, good question though, vectors. 3.1 is on vectors in 2 space, 3 space, and n space. So, so vectors are represented in 2 dimensions or 2 space, or 3 dimensions or 3 space by arrows. Okay, so you've probably seen this before. Maybe if you've taken physics, you've seen vectors represented as arrows. Okay, so the direction of the arrowhead specifies the direction of the vector, and the length of the arrow specifies the magnitude. Okay, so when you start out learning about vectors, this is how you learn about them. More generally, vectors don't have to be this, but at the moment they are. Okay, so if you keep going in mathematics, you'll have to open your mind up to more general definitions of vectors. But right now we're keeping it simple. Okay, so a vector is represented in 2 or 3 dimensions by arrows. The direction of the arrowhead tells you the direction of the vector, and the length of the arrow tells you the magnitude of the vector. Okay. Okay. So we call, so mathematicians call these geometric vectors. Okay. The tail of the arrow is called the initial point. The tip of the arrow is called the terminal point. Okay, so the point where it has the arrow, that's the terminal point, right? So here, without, okay, see that arrow there? If we had a vector that looked like that, right? The right side would be, all right, so for this vector, the right side is the terminal point. And the left side is the initial point. Okay. It's not always right and left, but if the arrow is pointing to the left, then the terminal point would be to the left. Okay. So we denote vectors in bold space time, okay, such as, and so I'm going to bold these in A, B, B, W, and X. Okay, so here's I'm going to put bold. Okay, so vectors will often bolded like that, okay, to differentiate them from a regular letter. Okay, and we denote scalars in lowercase, italic type, such as so A, K, B, W, and X, and so it might be italicized there. Okay, if we don't have a lot of time, I may not be able to bold everything in, but gives you an idea how you can differentiate between vectors and scalars, okay? But I'll make it clear what we're talking about. Okay, so when we want to indicate vector B, its initial point A, and terminal point B, then we write, and so then we'll write V as equaling to AB with an arrow above it. Okay, like that. Okay, so then that denotes that we have a vector where the initial point is A and the terminal point is B. So that's the direction the arrow is going above it. See that? Okay. And so that just represents a vector with initial point A and terminal point B. So very simple drawing. Here's a vector. If this is the initial point A and the terminal point B, then this is the vector AB. All right. Okay. Vectors with the same length and direction are said to be equivalent. Okay, and equivalent vectors are said to be equal. Okay, by writing V equals W. Okay, so what we're doing is we're changing the meaning of same to mean the same direction and same magnitude. Okay, so that's a vector AB. So if you have a vector here, if you have a vector here, right, and you have a vector here, okay, and I'm drawing it in such a way it may not be the exact same size. So what I'm doing is I'm saying that I'm making it the same size in the same direction. So this vector V here is equal to that vector W there. So this is vector W. This is vector V. So these two vectors are considered equal, even though they're in two different places. Where they are doesn't matter. What matters is their magnitude and direction. Okay. The zero vector has the same initial and terminal point because its length is 0. Okay, so it starts and ends at the same place because it doesn't go anywhere. Okay. So the zero vector can be assigned any direction that is convenient. for the problem at hand. Okay, so unique to the zero vector is that it doesn't matter what the direction of it. Okay, and so two zero vectors are the same or equal, even if they have different directions. That's only true for the zero. And so you may need, for a particular problem, you may need a direction, a certain direction. And so if you have a zero vector, you can just assign it that direction, and that's the same vector, regardless of the direction. Okay, so there's a few rules I'm pretty quickly going to go over. So this is the parallelogram rule for vector addition. Okay, so if V and W are vectors in 2 space or 3 space, or each in 2 space or each in 3 space, so that are positioned so that their initial points coincide, then the 2 vectors form adjacent sides of a parallelogram, and the sum B plus W is the vector represented by the arrow from the common initial point of B and W to the opposite vertex of the parallelogram. Okay, I was just spelling parallelogram quickly. Okay, so parallelogram rule for vector addition. If V and W are vectors in 2 space or 3 space that are positioned so that their initial points coincide, then the 2 vectors form adjacent sides of a parallelogram, and the sum B plus W is the vector represented by the arrow from the common initial point V and W to the opposite vertex of the parallelogram. Okay, so this is explained very easily with a picture. If you have a vector V here and you have a vector W here, and they form adjacent sides of a parallelogram because they have the same initial point, that's the common initial point of V and W, then they're adjacent sides to a parallelogram. Right? So there's exactly one parallelogram that can be formed from these 2 adjacent vectors where they are 2 sides of that parallelogram, 2 adjacent sides of that parallelogram. Okay, only one. Okay, and so now this is the unique parallelogram that can be formed in this way. And so the vector V plus W is equal to the vector going from the common initial point of V plus W, V and W, to the opposite endpoint of the parallelogram. So this is the vector V plus W. Okay, and so by that definition, by that parallelogram rule, that we can define V plus W in that way. All right. So you can also see it as, well, if you thought of moving V over, sliding it over along W, this would be V, right? And if we took the vector W and slid it along the vector V, then this would be W, right? So you could think of getting to this point by starting at the common initial point, moving along the vector V, then moving along the vector W to give you V plus W. Or you can move along the vector W, then along the vector V and get W plus V, which is the same as V plus W. So there's several perspectives of looking at this picture. So this perspective as the diagonal of the parallelogram this is illustrating the parallelogram rule for vector addition. Okay, so that illustrates the parallelogram rule for vector addition, that sum of 2 vectors is the diagonal of that parallelogram. The next rule is the triangle rule for vector addition. Okay, that says if V and W are vectors in 2 space or 3 space, so this argument holds for 3 space also, 2 or 3 space, So V and W are vectors in 2 or 3 space that are positioned. So the initial point of W is the terminal point of V, then the sum V plus W is represented by the arrow from the initial point V to the terminal point of W, to the initial from the initial point of V to the terminal point of W. So this is called the triangle rule for vector addition. If V and W are vectors in 2 space or 3 space that are positioned at the initial point of W is the terminal point of V. The sum V plus W is represented by the arrow from the initial point of V to the terminal point of W. Okay, so what that means is that if you have a starting vector V, and you have, this is the initial point, right? And this is the terminal point. This is the terminal point of V. So if you attach W to the terminal point of V, where you take the initial point of W and attach it to the terminal point of V, then V plus W is defined as the vector starting with the initial point of V to the terminal point of W. And so you can define V plus W, the same V plus W, in another way as being that vector. So this is vector V plus W formed in that way. So this is a second way to define the vector V plus W. Okay, and so this is from the triangle rule for vector addition. Okay, so now V plus W is also defined that way. Okay, so important is that adding vectors is a commutative operation. V plus W equals W plus V. So I'm going to denote this by 1 in case I need it later. So, so the above equation says that vector addition is a commutative operation. Okay, it doesn't matter the order that you add. It does not matter which vector comes first. Okay, so V plus W equals W plus V. That's called commutativity of vector addition. The next idea is vector addition viewed as translation. So if V, W, and V plus W are positioned so their initial points coincide, then the terminal point of V plus W can be viewed in 2 ways. Way one. The terminal point of V plus W is the point that results when the terminal point of V is translated in the direction of W by a distance equal to the length of W. Okay, so if V, W, and V plus W, all 3 of them are positioned so their initial points coincide, then the terminal point of V plus W can be viewed in 2 ways. The terminal point of V plus W is the point that results from the terminal point of V is translated in the direction of W by a distance equal to the length of W. Okay, so now you have your same vectors, V. You have your same three vectors. That's V again. Wait, it's gonna go slightly to the right. That's vector V again. This is vector W again. This is the vector V plus W again. Let's say we look at all three of those vectors. They're all from the same point. Okay, so they all have the same initial point. Now, you can think of V plus W, the terminal point of V plus W, if you're starting at the same initial point here. You can think of the terminal point of V plus W as being the point that if you took the terminal point of V and you translated it in the direction of W. So see that this is the direction of W, right? That's the direction of W. But it's a distance, the length of W. So you're going to go in the direction of W. That's the direction of W, right? That's the direction of W. But then we're going to go along that direction, the length of W. And so we're going to keep going in that direction as long as the length of W. Now, when we do that, the exact point we reach is the terminal point of V plus W. That's what the next thing says. So this is part A of this is vector addition. Viewed as translation. Okay, so this is vector addition viewed as translation, and specifically, this is the first way to view it. Okay, so there's two ways there. So this is the first way to view it. That you move along V first, and you take the terminal point of V, and you move it in the direction of W, the length of W, to get to the terminal point of V plus W. Okay, there's also a second way to view it that I'm going to write down. So the second way I'm going to illustrate here. So this is the second way to view it. So before I put that picture in, I'm going to go back to Word and I'm going to type it in here. So the second way to view it is that the terminal point of V plus W is the point that results when the terminal point of W is translated in the direction of V by a distance equal to the length of V. So 2, the terminal point of V plus W is the point that results when the terminal point of W is translated in the direction of V by distance equal to length V. Okay, so basically, you have the same vectors. You have the vector V, you have the vector W, you have the vector V plus W, okay, that's a straight line. Okay, so then if you start at the terminal point of W and you move in the direction of V, so this is the direction of V, right? So if you go in the direction, this is the direction of V. So in the direction of V, that's the direction of V. But then if you go along the direction of V, the length of V, which I'm using this absolute value sign to denote, you go in the direction of, from the terminal point of W, you go in the direction of V for length V, then you end up at the terminal point of V plus W. And so we can think of V plus W as you have your initial point of all three vectors. And if you go to the terminal point of W, then move the terminal point of W in the direction of V, a length of V, you end up at the terminal point of V plus W. And so the vector starting at the common initial point to that final terminal point is the vector V plus W. That's the second way to view it. There's a second way to view vector addition as a translation. You can either move along V first and then in the direction of W, the length of W, or you could move along vector W, then move in the direction of vector V of length V to get to the terminal point. So there's two ways to think. Okay, so all three, those two ways, this and this, there's three pictures illustrating that picture, this picture, and those two. Those four illustrate vector addition in four ways. Okay. So that's vector addition. Then there's also vector subtraction. Vector subtraction. The negation of a vector V denoted by negative V is the vector that has the same length as V but is opposite in direction. Okay. The difference of V from W denoted by W minus V, V from W, is taken to be the sum. So W minus V is equal to W plus the vector negative V. Negative V. So W minus V is equal to the sum of the vectors W plus negative V. So in this way, we define subtraction as vector subtraction using vector addition. So vector subtraction is derived from vector addition. Okay. So for instance, visually, if you have a vector, you have this pink vector W, and you have this blue vector V, then W minus V is equal to W plus negative V. And so we had four ways to define addition of vectors. And so W minus V is just adding the vectors W plus minus V. So any of the four ways works. So let's say you have W, vector W here, right? And so you have its initial point, and you have the initial point of W, and you have the terminal point of W. Now you have vector V, but what's negative V? Negative V is the same length vector, but opposite in direction. So negative V is just the same length, but opposite direction. And so you want to add negative V to that vector. And so you attach it to the terminal point of V, and now you're adding the vector negative V to W. And so you're starting at the same, you're making them have the same, you're taking the initial point of negative V to be the terminal point of W. And so you're adding negative V to W. And so now the terminal point of this, I'm going to have, the arrow just went. Okay, so the arrow at the end here. Okay, so this is negative V. And so, right, the initial point of negative V is at the terminal point of V. They meet the same spot. It's not a different spot. And so then the final vector W minus V is the vector that starts at the initial point of W and ends on the terminal point of negative V. So that's the vector W minus V. W plus negative V. it has that directional, so the arrow is pointing to directly exactly the terminal point of negative b. Okay, so now we've also defined vector subtraction by vector addition. There's also scalar multiplication of vectors. So if v is a non-zero vector in 2 space or 3 space, and if k is a non-zero scalar, then we define the scalar product of v by k to be the vector whose length is the absolute value of k times the length of v, and whose direction is the same as the direction of v if k is positive and opposite in direction if k is negative. Okay, and if k equals 0, then 0 times the vector gives you the 0 vector, and then the direction doesn't matter. Okay, if k equals 0 or the vector v that you're multiplying constant is already 0, then we define kv to be the 0 vector. Okay. And also, if you take -1 and multiply it by b, that's negative b equals negative b. Okay, so -1 times b is negative b, is the vector negative b from before. And I'm denoting this with a 3 because that's, and then this is 2. Okay, I'm not multiplying by these numbers, I'm just indexing for reference. Okay, so -1 times b is equal to negative. Okay, so back to the whiteboard. So for instance, if you have, so if you have a vector v, right, that's our vector v, then if you just, same direction but half its magnitude, that's half v, because that's half of the length. Then if you take the same vector and just go the opposite direction, that's negative v, right? But negative v is the same as -1 times v. If you double the length of v, right, that would be 2v. If you triple the length of v but go in the opposite direction, you triple the length of v but then go in the opposite direction. So this is exaggerated, it's more than 3v, I think, but you get the idea, right? So there's nothing special about the arrow, I just wanted the arrow to hint at the point of that line. Okay, so then that's all right, so that, okay, so that's just an arrow. Okay, so then that's 3v, let's say. So oh, sorry, that's -3. -3v because it's the opposite direction. Okay, so 3 times magnitude but opposite direction, -3. Okay, okay, so back here. So suppose v and w are vectors in 2 space or 3 space with a common initial point. If one of the vectors is a scalar multiple of the other, then the vectors lie on the same line and are thus called collinear. Okay, parallel lines are also said to be collinear, and vice versa. Okay, meaning collinear lines parallel. Okay, so remember, it doesn't matter where a vector is. Okay, so vectors are equivalent if they have the same direction, same magnitude. So when we say two vectors are equal or equivalent, nowhere does it matter where it is. So and so when you have two lines that are okay, so starting at the beginning, if you have two vectors with the same initial point, so that's v, let's say, and then same but one is a constant multiple of the other. Then let's say this is negative 2v. So this is negative 2 times v. So the blue vector is a constant multiple of the green vector. Then they're collinear because they're both, they fall, there's a line in which they're both on. Right? So v and negative 2v are collinear. Okay. Now, if you have vectors that are parallel, then, so if you have a vector here, right? If you have a vector here and you have a vector here, right? So these are parallel, right? Okay, but because they're parallel, if you move one of them, right? So if you move this vector, and by moving it, you're not changing the vector. So this vector is still the same vector. Okay, and so now I move the pink vector over there and they're collinear. They're on the same line. And so parallel vectors, parallel implies collinear. Okay, and if they're collinear, you can move them and they're parallel. Right, and collinear also implies parallel. All right, so they each imply the other. Okay, so next is the associative law for addition of vectors. Okay, and so that law says that u plus v plus w is equal to u plus v plus w to u. Okay, so u plus v plus w equals u plus v plus w. The parentheses are telling you what to add first. So that's v plus w first, then u plus that sum. This is u plus v first, and then that sum plus w. And so that's the associative law. Those two are equal. Okay. So we can see the associative law by the following picture. Okay, so here I'm going to illustrate the associative law. So an illustration of the associative law for addition of vectors. So if you start with the vector u, which I'm gonna start with pink. And then another vector v in blue. And then so then if you have u and v there, then u plus v we already know is going to be this vector, right? Where it ends at the same point, not past it. Okay, so that's u plus v. Okay, and so then after that, we had w. So let's say you add w, and this is w. So the vector, so if I start at the starting point here, right? And first I do u plus v, right? U plus v would get me here. And then I add w afterwards. So that's u plus v first and then w. So the vector that goes from here to here, one way to view it is you take u plus v first and then add w. So u plus v in parentheses and then plus w. See how we go along the black arrow u plus v and then along the green arrow w? So that's u plus v plus w. Another way is we do v plus w first. But so if we do v plus w first, then let me see if I can do this all in one picture. So if we do v plus w first, then we move along this vector, which is vector v. Then we move along the next vector w, right? And so if that's v, so the vector that goes from the same initial point as before, but now to that point here, that's the vector v plus w, right? So if you take v plus w first, you'd be going from the initial point to that new final point there. That's v plus w. And then afterwards, if you do u plus that vector, so if you do, okay, so if you do u plus, so you do v plus w and then u, then okay, so then this triangle I just drew, I'd really want this first, but u is going to be added first. So I'm going to modify. So see that triangle there? I'm going to move it. I'm going to move that triangle, which is v plus w. I'm just going to move it so that it's here. You see that? So this vector is v plus w. Okay, I'm going to rewrite v plus w so that it's in its own unique spot. I'm by this arrow here. This is v plus w. So I'm moving the triangle with blue, green, and black vertices upright. So the v plus w vector is there. So I'm going to erase this, erase this, erase this. So I just writing v plus w. It's the same vector. It's first v and then w. So v plus w starts here. You go along v and along w. But if you do v plus w and then u, then the same vector at the bottom is u plus v plus w. Okay, so you're technically adding v plus w first, but then in order to get there, you start at u. So you go u and then plus v plus w. See that? So first along the pink vector, then along the black vector, u plus w gets you to the same point as the black vector u plus v plus the green vector w. So u plus v plus w equals u plus v plus w. Okay, so that illustrates the associative law for addition of vectors. So specifically, it illustrates that here for these vectors, u plus v plus w is equal to u plus v plus w. Okay. Okay, so then that explains that. Okay, so if a vector in n space is positioned with its initial point at the origin of a rectangular coordinate system, then the vector is completely determined by the coordinates of its terminal point. We call these coordinates the components of V relative to the coordinate system. V equals the vector V1, comma V2. Denotes a vector in 2 space denotes a vector V in 2 space whose coordinates are whose first coordinate is V1 and whose second coordinate is V2. Okay. Also, the vector V equals the vector V1, comma V2, comma V3 denotes a vector V in 3 space whose first coordinate is V1, whose second coordinate is V2, and whose third coordinate is V3. Okay. It's a fact. 2 vectors are equal if and only if their corresponding components are equal. Okay, so 2 vectors are equal if and only if their corresponding components are equal. So as an example, the vector V1, comma V2, comma V3 is equal to the vector W1, comma W2, comma W3 if only if V1 equals W1 and V2 equals W2 and V3 equals W3. Another way to write V1, V2, V3 equals W, and W3 is right, V equals W. Right? So you could have also written it that way. Okay. So that's an example of saying 2 vectors are equal if only if their corresponding components are equal. These are vectors in 3 space. And so 2 vectors in 3 space, V and W, are equal if only if their corresponding components are equal. V1 equals V2 and V2 equals V3 and V3 equals V4. And V1 equals W1 and V2 equals W2 and V3 equals W. If any one pair of components, corresponding components, are not the same, then the entire vectors are not equal. Okay, so another example, the vector 1, 1, 1, 7 is not equal to the vector 1, 1, 1, 3. Even though the first three components are the same, the fourth component is different. All four components have to be the same. If all four corresponding components have to be the same in order for the two vectors to be equal, if any one is different, if any one pair of components is different, that means that they're not equal. Okay. So if you have your x-axis, you have your y-axis. And so if you have a point, you can label it as v1, comma v2. Right, but that point can be associated with a vector starting at the origin. And so that vector starting at the origin is determined by its terminal point. And so the point, the notation v1, comma v2 can also be used as notation for a vector that starts at the origin and whose terminal point is the point v1, comma v2. So the ordered pair v1, comma v2 with the subscript. The ordered pair v1, comma v2 can represent a point or a vector. Okay, so you might normally use it as a point. Now you can also think of it as a vector, the vector corresponding with the vector starting at the origin, ending at that point. Right, so even though a point is not a vector, you're technically saying a point is a vector. A vector is a point because of that association. Okay. Okay, so next, so if the vector PQ denotes the vector with initial point P1 of x1, comma y1, and terminal point P2 of x2, comma y2, then the components of this vector are given by the formula. So the vector P1, the vector PQ is equal to the vector whose coordinates are x2 minus x1, comma y2 minus y1. Okay, so a picture illustrates that. So if you have a vector, okay, so you have your x-axis, you have your y-axis, and so you have a point P1 whose coordinates are x1, comma y1, and you have a terminal point, which is the point P2 at x2, comma y2. Then you can think of that as being, and so the vector, this vector is P1, P2. It starts at point P1, ends at point P2 in that direction because the arrow. And so if you want to think about its components, okay, so we try to just in parallel with the x-axis and this in parallel with the y-axis. So you'd want to ask yourself, okay, well, what's the length? What is the length of this? Well, if the x coordinate of P2 is x2, you're taking the x coordinate of P2, which is here, and you're subtracting from it the x coordinates of P1. You're subtracting from it the x coordinate of P1, which is x1. And so this distance is just x2 minus x1. Okay? So this distance is just x2 minus x1. Okay, so that the distance there is x2, x1 is larger because it's to the right. Then this distance is just, well, the y coordinate of P2 is y2, and the y coordinate of P1 is y1. Right, so if you have this, then this y distance is y2 minus y1. Okay, so that means that now you can think of this vector as moving to the right, x2 minus x1, and moving up, y2 minus y1. And so P1 comma P2 is equal to the vector x2 minus x1, comma y2 minus y1. Okay, that's all. Okay, so okay, and then just the same idea, but just in 3 space. I'm just going to write down over here. So the components of a vector in 3 space that has initial point P1, x1, y1, z1, and terminal point P2, x2, y2, z2 are given by, okay, so it's given by P1, P2, vector P1, P2, whose coordinates are x2 minus x1, comma y2 minus y1, comma z2 minus z1. Okay, so it's just very similar to this, except now we're living in 3 space. I drew a picture to illustrate that. Okay, so an example. Example 1 is, let's say you have initial point. Initial point is P1, which is coordinates 2, -1, 4. And you have terminal point, which is P2, which is 7, 5, -8. And the vector V is equal to this vector. And so that vector is, so you take the terminal point of P2, you take 7 minus 2, comma 5 minus -1, comma -8 minus 4. And so then this is equal to 5, comma 6, comma -12. Okay, so you just take the difference of x coordinates, difference of y coordinates, difference of z coordinates, but you make sure you choose the order correctly so that you're taking the coordinates, you're taking each coordinate of P2 and subtracting the coordinates corresponding component of P1, right? That's because in our rotation, we said we're going from P1 to P2. And so the subtraction is in the opposite direction. We take a number in P2 and subtract from it the corresponding number from P1 for each coordinate, and then we get the vector with that initial point and that terminal point. So that's example 1. Okay, definition 1. If n is a positive integer, then an ordered n tuple is a sequence of n real numbers v1, v2, vn. Third, the set of all n tuples is called n space and is denoted by r superscript n. Okay, so if n is a positive integer, an ordered n tuple is a sequence of n real numbers v1 to vn. The set of all n tuples is called n space and is denoted by r. Okay, so example, the ordered pair 1, 2, right, is an ordered 2 tuple. 1 is its first coordinate. 2 is its second coordinate. Okay, as a vector, the vector 1, 2 is in 2 space or in R2. Okay. Also, R2 is equal to the space of all 2 tuples. Or, in other words, R2 is equal to the set of all ordered pairs A, B, such that A and B are both real numbers. Okay, so R squared is equal to set of all A, B, such that A and B are both real numbers, right? Right. Another example, R3 is then equal to the set of all A, B, C, such that A and B and C are real numbers. Okay, so R3 is the space of all 3 tuples. R2 is the space of all 2 tuples, where in both cases the components are real numbers because it's R squared, R cubed, right? And then another more general example, Rn, which is n space, is the set of all ordered n tuples. So this would be A1, A2, A3, an, such that A1, A2, A3, up to including An are all real numbers. Okay, so n space is a set of all n tuples. It's a set of all ordered n triples. Ordered n tuples where there are n components and each component is a real number. The set of all ways to do that. That's Rn. Okay, those are examples of n space and the elements of n space. Okay, so definition 2. Vectors v, which equals v1, v2, vn, vectors v and w, which is equal to the vector w1, w2, w3, wn in Rn are said to be equivalent, also called equal, if V1 equals W1, and V2 equals W2, and V3 equals W3, and dot, 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 and Vn equals Wn. Okay, so we were saying before how corresponding components have to be the same for two vectors to equal. It's the same thing here for vectors in n space. We have two vectors in n space. Saying that they're equal means that each of their corresponding components are the same or equal. Okay, so we indicate that two vectors, v and w, are equivalent in this way from this definition by writing v equals w. Right, just a normal way to write it. Okay, so v equals w means that as vectors v and w vectors in n space, their corresponding components are equal. Okay, example 2. Okay, so if you have the vector a, b, c, d is equal to the vector 1, -4, 2, 7. That's true if and only if a is equal to 1, b is equal to -4, c is equal to 2, and d is equal to 7. Okay, so this is another interesting case where you have one equation which leads to 4 equations. So we see this all the time. So if you have this one equation is equal, then you have, well, in this class we see this all the time. So where we have this one equation, and equivalently we have 4 equations. Okay. Okay. Definition 3. If v, which is equal to the vector v1, v2, v3, dot, 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 vn, and w, which is equal to the vector w1, w2, w3, dot, 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 wn. So if those are two vectors, v is that, and w is that, are vectors in Rn. And if k is any scalar, then we define the following. v plus w is equal to taking the sums of their corresponding components as the components of the new vector. So v1 plus w1 is the first component. v2 plus w2 is the second component. v3 plus w3 is the third component, dot, dot, dot. vn plus wn is the nth component. That's v plus w. kv is a constant multiple k times vector v. So the first component is kv1, the second component is kv2, the third component is kv3, dot, 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 and the nth component is kvn. So that defines kv. Negative v is the negative of the vector v, right? That's the same as earlier as -1 times v. And that's equal to, just take the negative of each component. So negative v1, comma, negative v2, comma, negative v3, comma, dot, 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 comma, negative vn. I could have written -1 times each component, but I just wrote the negative sign instead. Okay, and then w minus v, remember before, is equal to w plus negative v. And so by vector addition that we already did up here, v plus w, we apply it to v plus minus w. And so the first component is w1 plus negative w1 plus negative v1. The second component is w2 plus negative v2. Third component is w3 plus negative v3 dot 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 to including the last component, the nth component wn plus negative vn. And so this is equal to, well, the first component is w1 minus v1. Second component is w2 minus v2. Third component is w3 minus v3, comma, dot, 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 comma. Last, the nth component is wn minus vn. And so that defines w minus v. It's this. Okay. Okay, so that's definition 3. And example 3, we have given that the vector v is equal to the vector 1, negative 3, 2. And w is equal to the vector 4, 2, 1. What that means is that v plus w is just equal to, you just add the corresponding components. You have 1 plus 4, comma, negative 3 plus 2, comma, 2 plus 1. And so that's equal to 5, comma, negative 1, comma, 3. 2v is equal to, so it's 2 times the vector v, which is 1, comma, negative 3, comma, 2. And that's equal to multiplying each component by 2. So it's 2, comma, negative 6, comma, 4. Negative w is equal to the negative of the vector w, which is 4, 2, 1. It's just negating each component. So you have negative 4, comma, negative 2, comma, negative 1. And you have the vector v minus w, which is equal to the vector v, which is 1, negative 3, 2, minus the vector w, which is 4, 2, 1. And so then that's equal to just 1 minus 4, comma, negative 3 minus 2, comma, 2 minus 1. And so that's equal to negative 3, comma, negative 5, comma, 1. Okay, so you have all 4. And so each of them are from definition 3. Okay, all 4 of them are from definition. All 4 of them are from definition 3. Okay. Okay, so next is theorem 3.1.1 says if u, v, w are vectors in Rn, and if k and m are scalars, then a, u plus v equals v plus u. B, u plus v plus w is equal to u plus v plus w. C, u plus 0 is equal to 0 plus u, which equals u. D, u plus negative u is equal to 0. E, k times u plus v is equal to ku plus kv. F, k plus m times u is equal to ku plus mu. And G, k times mu is equal to km times u. And H, 1u equals u. This is theorem 3.1.1. If u, v, and w are vectors in Rn, and if k and m are scalars, then you have a through h here. Okay, so this is just commutativity, A. B is associativity. C is called 0 is an identity, but if you add 0 to any vector, you get that vector back. So u plus 0 equals 0 plus u equals u. If you take a vector and add its negative, you get 0. if you can left distribute a constant. So here k is a constant. So k times the sum of vectors is the sum of the constant multiples of those vectors. So ku plus kv. K times u plus v equals ku plus kv. If you take two scalars, k and m are scalars. If you take the sum of two scalars and multiply it by a vector u, then it's equal to ku plus mu. Then if you take a scalar k times a scalar multiple of u, mu, so k times mu, instead of multiplying u by scalar m and then by scalar k, you can multiply the two scalars k times m and then multiply u by the scalar multiple km, the product of the two scalar multiples. So you can change this order also, and they're still equal. And then h just says that 1 times the vector u is equal to that same vector u. So 1u equals u. So that's part h. So that's theorem 3.1.1. The next one is theorem 3.1.2. If v is a vector in Rn and k is a scalar, then a 0v equals 0. B, k times 0 equals 0. C, negative 1 times v is equal to negative v. Okay, so this is another case of where you have to think about what 0 means. Okay, here 0 is a scalar. Okay, so it's the scalar 0 times v is equal to the 0 vector. So on the right, this is a 0 vector. To the left, 0 scalar. Okay, the way you can see the difference is that you start with 0 as a number and you're multiplying it by a vector v, because normally you have the scalar next to the vector. So for instance, you might write 3v or 2v. 0v would typically mean 0, the number 0 times v. But if you multiply a scalar by a vector, the result is a vector. And so to the right, because you're saying this is a number 0 multiplying the vector by v, knowing the result has to be a vector, that means the right 0 has to be a vector 0. Here, you have a vector 0 and you're multiplying it by a scalar k. Typically, k is a scalar, and you would multiply a vector by a scalar, and you might write it this way. So 0 is a vector, and you're multiplying it by a scalar k. The result is still a vector, and so the right is also a vector. So in B, both zeros are vectors. In A, the left one is a number, and the right one is a vector. C, negative 1 times v is equal to negative v. There's no zeros there, so this, okay. So math is sort of kind of linearly, where you're starting from the beginning and you move forward. So you start with 0v, where 0 is a number, and then it equals 0. And so that means that the result is a vector, which means that the next 0 is a vector. If you start with the right side and you look at it as 0, then is it a vector or is it a number? You don't know. But if you start from the left, 0v equals 0, then you're saying a vector is equal to 0. So 0 is a vector. Okay, so the order in which you read things matters. Okay, so next is going to be calculating without components. Okay, so let's say you have x plus a is equal to b, and let's say this is given. Okay, so let's say this is given to you, and these are vectors. So you want to compute the vector x as an unknown vector in that equation, but without components. So we're not talking about the components of the vectors that we're adding. We're just adding them vector by vector. So you can think of that as taking the vector x plus a and then adding to it negative a. And that would then equal b plus negative a. So I just added negative a on both sides. I'm going to make this centered. Okay, so x plus a equals b is given. Then you get this, and so you get this by adding negative a to both sides. Okay, so I added negative a to both sides, and now I have x plus a plus negative a equals b plus negative a. Then I can think of the left side as x plus a plus negative a. And I can think of the right side as just equal to b minus a. And so this is because of associativity of vector addition, or theorem 3.1.1, part B. Okay, so theorem 3.1.1 part B is this. It's associativity. It's saying u plus v plus w equals u plus v plus w. You can change the order of the addition. So here we change the order. Instead of x plus a plus negative a, it's x plus a plus negative a. So that's by associativity, that this quantity is the same as this quantity. And so b plus negative a is just b minus a by definition. Okay. Okay, so note that b plus negative a is equal to b minus a by definition. That's how we defined subtraction of vectors as being one vector plus the negative of the other. And so continuing, jumping over that note, you have x plus 0 is equal to b minus a, because the a plus negative a is 0. And so this is by theorem. This is by theorem still 3.1.1, but now it's part D. Part D says a vector plus its negative is 0. So here instead of u, it's called a. So this is by part D of that theorem. By theorem 3.1.1 D. Saying of x plus 0 is equal to b minus a, but that's x equals b minus a. And so this is by also theorem 3.1.1. But what we're saying now is a vector plus zeros itself. X plus 0 equals 0. This is part C, where u plus 0 equals u, 0 plus u equals u. This is part C of that theorem. And so this is part C here. Okay, so now we have x equals b minus a. And so what we concluded is that our vector x is the vector b minus a, but we did it with calculating without using components. So we never thought about the components of any of the vectors involved. We just solved it in terms of vectors. Okay. So this is definition 4. So if W is a vector in Rn, then W is said to be a linear combination of the vectors v1, v2, dot, 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 vn, sorry, vr. If W is a vector in n space, then W is said to be a linear combination of those R vectors in Rn if it can be expressed in the form. So what you want to do is you want to say this vector W is a linear combination of the vectors v1 to vr. And so you're going to write as k1 v1 plus k2 v2 plus k3 v3 plus dot, 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 plus kr vr. I'm not multiplying by this, I'm just denoting it. The book it's denoted as 14, so I'm going to use the same number. Where K1, K2, K3, dot, 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 K sub R are scalars. These scalars are called coefficients of the linear combination. Okay, they're called coefficients of the linear combination. If v equals 1, if r equals 1, then 14, equation 14 becomes W equals K1 B1. So that a linear combination of a single vector is a scalar multiple of that vector. Okay, so definition 4 is defining a linear combination of vectors. I would extend the line further, but the line would then interrupt with the letters here. So I want you to be able to see the B's. Okay, so if W is a vector in Rn, and W is said to be a linear combination of the vectors v1, v2 to vr in Rn, if it can be expressed in the form W equals K1 v1 plus K2 v2 plus K3 v3 plus dot 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 plus Kr vr, where the K's are all scalars. And these scalars are called coefficients of the linear combination. Okay, so let me give you an example. So for instance, let's say you have a vector, v1, and it's equal to the vector 1, 1. And you have a vector v2, and it's equal to the vector 2, 2. Then we say that then we can express the vector 3, 3. We can express the vector W equals v 3, 3 as a linear combination of v1 and v2 in the following way. Okay, so the vector W, which is 3, 3, is equal to 1 times the vector 1, 1 plus 1 times the vector 2, 2, which is equal to 1 times v1 plus 1 times v2. So here this vector 3, 3 is written as 1 times the first vector plus 1 times the second vector. So W is equal to 1 v1 plus 1 v2. And so here W is expressed as a linear combination of v1 and v2. Okay, so a linear combination of v1 and v2 is this expression. 1 v1 plus 1 v2 is a linear combination of v1 v2. And so we're expressing W as a linear combination of v1 and v2. Make sense? Okay. So that's an example of a linear combination of two vectors. Okay, and the coefficients here are 1 and 1. So both these ones are coefficients of that linear combination. Okay, so another idea. So a new thought. Okay, so vectors in n space can be written as v is equal to v1, comma v2, comma v3, comma dot dot dot, comma vn, which is called comma delimited form. Okay, so it's called comma delimited form. You can also write a vector. You can also as this form, where v is equal to bracket v1, comma v2, comma v3, comma dot dot dot, comma vn. And so this is called row vector form. Okay, and it could also be expressed as this form. So V could also be written as a column vector, column matrix. And so you could think of it as V1. Oh, but okay, so no commas. So this is a vector. This is a row vector. Okay. No problem. So here it's B2, B3, B, n. Okay, and so this is called column vector form. Okay, so that's called column vector form. So we have comma delimited form, we have row vector form, no commas, column vector form like that. They're all the same thing. They're all vector B. They're just different ways to illustrate the exact same vector. Okay, so this is the end of 3.1. Finished it just the end. So for homework, okay, so we covered all of the material for test 1 already because 2.3 was the last thing and we went over the homework, right? So test 1 is only in chapters 1 and 2. But we are starting to cover new material now. So I'm going to assign also for homework, for homework, I'm assigning exercise set 3.1 for homework. Okay, so this is on test 2. Okay, so this is not test 1 material. Okay, but I figure if we're covering stuff, it gives you some more time to study for the first exam if the exam is not right after we're done with it. Okay, so we're going to cover stuff in chapter 3 that's not on test 1, but you'll have plenty of time to make sure you know all the stuff that we went over. Okay. So before I answer that question, I'm just going to write down the homework. So it's 3.1, 11, 15. 3.1 is 3.1, 11, and 15. Okay, and so that's due next class on 11 to 2021. Okay, so that's the end. Three 3.1 and the homework is due next class in that. Okay, so 3.1, 11, 15. 3.1, 11, 15. Good. Okay, so that's okay. So the question was, do you think you give us a list of topics that will be in the exam? So, right. So that's test 2. Okay, so test 1. Right, you can see test 1 on the screen. Right? Review for test 1 on the screen. Right. These are all the sections that are on the exam. Right. So I wrote review, things to study, linear algebra review sheet for test 1. Things to study 1, chapter 1, systems of linear equations and matrices. Those 9 sections. 2, chapter 2, determinant. 2.1, 2.2, 2.3. Right. Review your lecture notes and homework notes. Also, so those are the sections you need to cover. Now, if there's a lot of material in those 12 sections. So as far, I wouldn't want to say that if I gave you a list that there couldn't also be something else that's not on the list, so to give you an idea of things you would need to study, I would say the review sheet does that. It has everything in it, but you might, you want to know reduced row echelon form. You want to know how to use Gauss-Jordan elimination, Gaussian elimination, right? Row echelon form. You need to know about elementary matrices. You need to know about elementary row operations. You need to know, how to find all the solutions to a linear system, how to express the solutions as parametric equations if there are infinitely many solutions, how to find the unique solution if there is one. The equivalence theorem is important. There's a lot of parts to it. You need to know how to find the determinant of a matrix. You need to know the adjoint of a matrix. You need to know how to, you need to know the cofactor expansion along a row or column. You need to know how to choose the right row or column so that finding the determinant is faster. You need to know how to find the determinant of a 2x2 matrix, the formula AD minus BC, right? A matrix is invertible if and only if its determinant is non-zero, right? And if in such a case, A inverse is equal to 1 over AD minus BC times the 2x2 matrix where you switch the column entries and you negate the off column entries, off main diagonal entries, right? So there's a lot of things to know. I said quickly, I said some of the things you need to know. I have office hour tomorrow, right? Every Friday, including tomorrow. So if you want me to specifically talk about things and if you want kind of me to say even more about topics, you can come to office hour and I can say more there. Kind of not much time to say it now. Yeah, there's a practice test online. So if you go to Blackboard, there's a practice test for test 1. You can take that, but you should take the practice test after you study, right? That should be the last thing you do, because the practice test is not every possible topic on the exam. The practice test is just to see whether or not you're ready to take the exam. So the first thing you should do is to study this review sheet, go over all the homework, and make sure you can do all the problems on the review sheet, right? And then once you feel you can, then you should take the practice test. So that should be the last thing you do before you take the exam. Okay? So I'll see all of you next class next Tuesday. Okay, don't forget about the homework for 3.1. Okay, good night. Yeah, everyone. Save the whiteboard. Night.